In this video, we're going to discuss the concept of modeling and why we are interested in modeling real-world phenomenon. And then after we've discussed the why, we're going to talk about how we begin to think about modeling real-world phenomenon. Basically, the whole course essentially leads up to these ideas in week 6 and 7, where we try to decide how to take those probabilistic concepts, the sampling distributions and confidence intervals and all of that information, and kind of put it into context of a sense of what am I trying to look at in the world and how can I model that in some sort of a mathematical framework, mathematical statistical framework. Now, that benefit of that framework is now I can potentially use that to either learn about why things happen the way they do or how they may happen in the future. Now, as we move forward, we'll start with a really nice quote here by George Box that talks about with modeling what we're really interested in. And the idea is that he says all models are wrong, but some are useful. And that's something we really need to get our mind around as we go through these last few sections, is that we realize and recognize the fact that the models, the mathematical formulation of our real-world phenomenon is not perfect. There are issues, there are gaps in how it works. It says here a model is a mathematical representation of the real-world phenomenon. It is not going to be perfect. However, we can leverage that to learn about the situation and learn how we can, again, predict the future, predict what may happen next or in certain circumstances. It's a formalized representation of a theory. Essentially, I'm taking these theoretical concepts that we've discussed and now formalizing it to describe what's happening in real life. Statistical modeling essentially is basically founded upon this idea that data that we have is really a function of two components. The first component is the fit. It's basically saying this is the true system, the true output, the true information that I'm trying to capture underneath this noisy data. Another time we would think of it as the signal in the system. The other component is the error in the system, the noise, the anything that's not explained in traditional methods here will be captured in the noise. Now, in a perfect world, we just get rid of the noise. We just say, forget about it. I want to focus on what's important. But trying to untangle the signal from the noise is very difficult. It's not easy, or it might even be impossible to do it. But with statistical techniques, we can quantify that noise and understand that noise via statistical distributions and leverage that to, again, help us extract what's really important. Inherent variation in a system is unavoidable. It exists. There's nothing we can do about it. So what we have to do, if we can't remove it, we need to learn from it and utilize that to help our understanding of the signal. You notice that what I have here is our data or our response, our Y, is simply broken down into our signal and noise. The signal is our fixed component that is usually a function of external data. So information from other inputs that help inform what's actually happening. And then we have our noise or our error that's just our the random component that's described probabilistically. Now, from that, we can say, okay, well, what's the simplest model that I could possibly come up with? Well, that's easy. The simplest model is basically saying Y, my output, is a constant plus some error. So, in other words, I'm assuming that the response is the same for every value, but there is some error which gives us variability. That constant I'm labeling as beta. Beta is my constant plus epsilon, which is my error. This is basically saying every point is the same value. It's actually the same thing, and we might see this probably next week, as the one sample t-test. We're basically saying every value is at an average, at a single number. We're going to use one number to predict for all of them, but then there's some noise in the system. Now you'd say, well, hey, this is perfect. We can actually model every single point as one constant value plus some error, if we know the errors, which of course we never really know the errors. So how do you find, why we don't have one value for the beta, for the parameter, how do you find the optimal value? How do we choose what value of beta will make this the most likely model. So how do we, first of all, that depends on how we model the errors. So our problem here is we're going to utilize the method of least squares. The problem is that our model is not perfect. There's nothing we can do. Errors exist. So what we're going to do as we try to predict the best value or model the best value of beta, we are going to minimize the errors. And this idea is essentially consistent throughout the next 2 weeks and actually consistent through all of statistical modeling in essence. We want to make our errors as small as possible. Pick the value of beta that allows my errors to be small. Now, once I have a value of y, the error is no longer random anymore. I actually know what the error is. It's a fixed instant. So what's really happening is my errors would be my data, my y, minus the fit, the beta. Now, of course, I don't know what beta is either. I have to choose what beta is. And my error term, if I give you beta, I can figure out the error term. It's the y minus my best guess, which is the beta in this case. So I really want to find out how to make those errors, those e's, as small as possible. Now, there's a big problem here. We might think, well, okay, let's just minimize the sum of the errors because every point has a different error. And unfortunately, that's not going to work because errors inherently can be positive or negative. If the data point is above my fitted value of beta, I have a positive error. If it's below, I have a negative error. And when I add them all up, actually in most cases I might get 0. And that doesn't really help me because I want to know not what the value that minimizes the errors as a number is. I want to know what value of beta minimizes the magnitude of the errors. So basically I want to get rid of the sign. Now most people would say, first thing I would guess is a lot of you would say, let's just minimize the sum of the absolute values. And that is actually a technique that works. You can do that. Now, it doesn't give us our traditional linear regression model or most traditional models, but it is allowable. It actually is not used in practice because the absolute value function is not differentiable at 0. Because of that non-differentiability, it becomes more mathematically complex. So because of that complexity, we don't want to add complexity, so we're going to avoid the absolute value. However, we could look at the sum of squared errors because square would also get rid of the sign. So that's going to be my goal. I want to minimize the sum of squared errors. Note I've underlined SSE because we refer to that often as SSE for sum of squared errors. This is also, as we said, known as the method of least squares. Why? Because I want to minimize, there's my least part, the squared errors. So it's the method of least squares. So let's return to our basic model and see how this applies. We want to find what value of beta minimizes the sum of squared errors. Well, if you go back to my initial equation, I said y equals beta plus epsilon I. yi equals beta plus epsilon I. Well, that means that epsilon I, or actually more importantly ei, is equal to yi minus beta. So what I'm going to do is I'm going to try to minimize the sum of squares. Minimize the sum of yi minus beta squared. Minimize that with respect to beta. Now I do have a short video proof available that'll be in the next video. But you can probably guess, if you had to pick one value that minimized this sum of squares, the most likely value of a set of points, it is going to be x bar. The constant value that minimizes the sum of squared differences from all points in a data set is the mean. So in other words, if I want those errors to be as small as possible, I'm going to replace beta with x bar. That is estimation from what we did last week. It's estimation applied to finding the minimum of the sum of squared error. Now, if you use a different criterion, like absolute value, for example, you didn't do squared, you did absolute value, you might not get the mean. It turns out, I believe, that if you used absolute value as your criterion, the number that minimizes the sum of absolute deviation is the median of the distribution. But for most of our cases here, we will focus on the sum of squared errors. We'll focus on minimizing that. And the next video will actually take you through that derivation. I'm not as incredibly concerned with the fact that you can recreate the derivation. I am more interested is, can you follow it? Remember our goal, let's summarize this whole video in one thing. Our goal here is to model the data. Find the signal that models some value y. My first model is I'm going to say every value is really the same with some error. So if every value is the same, I better try to estimate what that best value is. If I say I want to minimize the squared error, that best value is x bar. If I want to minimize the absolute error, it turns out to be the median. We will focus on simple least squares, and we'll be focusing on that in more complex models in the upcoming videos.